Hi guys, today we're going to learn about particle motion. So let's look at this example. A particle moves along an horizontal line so that its position at any time when t is greater or equal than 0 is given by s of t is equal to 2t power 3 minus 7 t power 2 plus 4 times t plus 5, where s is measured in meters and t is measured in seconds. So what are we going to do here? Since they gave you the equation of position, they are asking you to find the velocity at time t and at time t equals 1 second. So what we're going to do here is connect position with velocity. Velocity is going to be the derivative of position. With this idea, we can find velocity pretty easy from the equation of position. So you know that you are going to use the power rule. So what you're going to have here is you have 6t squared minus 14t plus 4. So this is going to be your beautiful equation for velocity. So the next thing that you inherit from the beginning of the problem is that the t must be greater or equal than 0. After that, what we're going to do is we're going to replace the t with the 1, so you have that velocity evaluated at 1 is going to be 6 times 1 squared minus 14 times 1 plus 4, and this is going to be equal to the beautiful number negative 4, and you know that this negative 4 is going to be in meters per second because those are the units that they gave you at the beginning of the problem. Please make sure that whenever you have a situation like this, you conclude with the correct units. Okay, so please remember that the connection here, velocity, is the derivative of position. Okay, so they ask you here, hey, when is the particle at rest? So what are you going to do here? Well, it's pretty similar to finding the critical numbers. Here what you need to set is your derivative equal to 0, which in this case we have that it's 6t squared minus 14t plus 4. Okay, you know that this is equal to 0, so what we're going to do here is you're going to factor out. I factor out the 2, so we have 3t squared minus 7t plus 2 is equal to 0. Then you can recognize that we can factor out the situation as 3t minus 1 and t minus 2. Okay, so having your t's being equal to 1/3 and 2. As you can see, both of the t's are positive, therefore they are in the domain of interest. The domain of interest is from 0 to infinity. Therefore, here we can conclude when the particle is at rest. Okay, we know that the particle, okay, is at rest, okay, at t equals 1/3 and 2 seconds. And since we need to justify, why do you know this? Because s of t is equal to 0 there. Now that's not it. You have a second piece. When the particle is moving to the right. So as we were analyzing the intervals for increasing, decreasing, here we're going to analyze the intervals for moving to the right and left. With this being said, you already found, technically speaking, the critical numbers, which are 1/3 and 2. Okay, so you build your table the same as before, like this, to infinity, and you're going to evaluate your s prime. So you can see that here your s prime, okay, remember we're evaluating here, okay, or here, wherever you want. Okay, you plug a number there, so what do you have here? This is going to be positive, this is going to be negative, and this is going to be positive, meaning your particle is moving to the right here, left here, and right here. Specifically speaking, for this question, they are asking you when this particle is moving to the right. So let's conclude on that. The particle, okay, is moving to the right when the derivative is positive. Okay, so to the right on the interval, you have that it's from 0 to 1/3 union to infinity, because s prime of t, which is equal to velocity, is greater than 0 there. Okay, so you have that. Okay, so that's your justification. You do need to say that the derivative is greater than 0 there. Okay, so hopefully it makes sense for you. Now, the next thing that we're going to do here is we're going to find acceleration at time t and at t equals 1 second. So what is acceleration? Similarly to velocity, you have that acceleration is going to be the derivative of velocity. In other words, it's going to be the second derivative of position. Okay, the great thing here is, let me put it here so strategically we can have the situation here. Okay, so you can see that here you have the derivative. Okay, so we're going to take the derivative of the derivative. So what's going to be that derivative? You know that it's going to be 12t minus 14. Okay, so this is your acceleration expression, and then at 1 you just replace the t for the 1, having 12 times 1 minus 14, which you know that it's going to be negative 2, excuse me. Okay, and this negative 2 is going to be meters per second square. Okay, so you can see that these are the units that we have because this is acceleration. Okay, so hopefully it makes sense from physics or some other class that you have taken before calculus. Okay, so now they ask you to find the displacement of the particle between t equals 0 and t equals 1.7 seconds, and you need to explain the meaning of your answer. So what are you going to do? Here, before you do a misinterpretation or something like that, okay, what is the displacement? If this is a particle, let's say that, okay, this is a particle, okay, and this is my initial point, okay, if I move from here to here, okay, and then I change direction and I rewalk this part, okay, and then I change direction and rewalk this part, and then this is going to be my final position. This is my initial position, this is my final position. So the displacement is going to be the distance between your final position and your initial position. This is going to be displacement. Okay? However, the total distance that you walk is very different from displacement. Why? Because when you were changing directions, you were rewalking the same area. Do you see it? So that's going to be total distance. So you can see that displacement is different than total distance. It might be the same in some cases, but most of the time it's going to be different. Okay, so what's going to be displacement here? You have that the displacement, okay, is going to be equal, okay, since that one is more simplistic, okay, displacement, okay, and here writing incorrectly displacement as usual, okay, so you have that displacement is going to be specifically from what was it, 0 to 1.7. I know that it's going to be s of 1.7 minus s of 0. So you need to be careful with the sign there. Okay, so what I'm going to do, I'm going to plug this equation in my calculator. Okay, let me get my calculator here, clean it up a little bit so you can see it. Okay, okay, so sorry about that. Let me go back. So I plug the equation here in my calculator. I call it s of x. So click enter, it's done. So what I did, I store my position function in my calculator. You can see that I store my position function there. Okay, so what I'm going to do here is I'm going to compute s of 1.7, okay, which they give me that it was 1.396, and then you have that s of, what was the other one, 0, okay, because it was my initial, it's 5. Okay, so you have that this, okay, minus 5, it's going to be equal to negative 3.604. Okay, obviously this is in meters. Okay, you're going to tell me how in the world this is negative. Well, I don't want the negative as a distance, but I want the negative knowing where my particle is at, and the negative is giving me that the particle is on the left side where I started. Okay, so since they are telling you to explain, that's why I wanted the negative. Okay, when I conclude, you'll see that I'm going to put positive. So you have that the displacement, what's the displacement, okay, of the particle, okay, you need to be very specific here because they are asking you to explain, right, between, okay, t equals 0 and t equals 1.7 seconds, okay, is, okay, 3.604 meters, okay, to the left, okay. So you can see that the negative is giving you beneficial information, which is telling you that it's to the left of where you started, right? So for part E, what we have to find is the distance traveled by the particle between t equals 0 and t equals 1.7 seconds. So what we have here is pretty straightforward. What you need to be careful is when the particle changes direction. So you need to know when the particle, okay, the derivative is equal to 0. Okay, so what we have is it was 6t squared minus 14t plus 4 equals 0, which in this case we already know that that's going to be in 1/3 and 2. Now, the 1/3 is inside this interval. The 2 is not inside this interval, so we eliminate that one. So pretty similar to the candidates test. What you're going to do is you're going to take your extremes here, evaluate your extremes, which are the 0 and the 1.7, which we already know because of the values from the displacement. So you have that this and this. So you have the 0, the 1.7, but in addition to that, we're going to have the 1/3. You know that when I plug the 0, I'm going to have that's going to be what? 5. Okay, and the 1.7, that's going to be 1.396. So when I plug the 1/3 in my calculator, the calculator gave me that it was, if you see it, 5.629. Okay, so let's plug that one. Okay, 6.29. Okay, and dot dot dot. So what we're going to do is we're going to compute the distance between this and this and this and this. So what I'm going to do, I take this one minus the 5. I have that the particle distance from here to here is 0.6296, and from this to, what do you have? That it's that one. It's this one minus this one that we have here. So that one is going to be 4.2336. So what we have here is that the total distance, okay, from 0 to 1.7 is going to be equal to this guy plus this guy. What I would do here, since you have the calculator, I would not round anything, and I would add both numbers fully. Okay, so as you can see, with all the decimal places here, and then you have the result. Your result here is going to be equal to 4.863. and more decimals, right? But we only care about the first 3 decimal places, so that one is in meters. And that's it for this problem, okay? For this part of the problem, what you have is the same equation. You have the same conditions, the same units, but they are asking when the particle is speeding up, and they want you to justify your answer. So the first thing that you need to recognize is, what is the meaning of a particle speeding up? So a particle is speeding up when velocity, both velocity and acceleration, have the same sign, meaning both are positive or both are negative. Now, slowing down, on the other hand, is when velocity and acceleration, they have opposite signs, meaning one is positive, the other one is negative. Now, so you can see what's the difference between speed and velocity. This is the graph of the quadratic function that we have. I think velocity, if I remember correctly, it was 6t squared minus 14t plus 4. So the equation would look like this, and the domain, it looks from 0 to infinity because we don't have time negative. So you can see that here the intercept is 1/3, the intercept here is going to be 2. So this is the graph of velocity. But what happens when you take the absolute value of the situation? So as you can see here, when you take the absolute value, all the negative part of this graph is going to be reflected over the x-axis. So is this part that you can see that you're like, what in the world happened to that? Well, it flipped because you have the absolute value. That's what the absolute value is doing to the velocity function. Here the x-intercepts here and here are 1/3 and 2, okay, and also this keeps going, okay. So that's what you have. This is your t, this is velocity, and this is going to be your t, and this is going to be technically speaking velocity, right? So that's what we have, okay. So to answer part F, what we're going to do, we're going to draw a double sign chart. Please note that it's double, showing both the signs of both velocity and acceleration, okay. So we already know that velocity, we already factor out this, and we found that the t, it was equal to 1/3 and 2 seconds. Similarly, at acceleration, we know that it's this one. Then if we solve for the situation, you have that it's 14/12, which we can simplify as 7/6, and that would be actually our technical possible critical numbers. Not critical numbers, possible inflection points, okay. So that would be it. Now, how can we build this famous double chart, okay? So what you're going to do is you start at 0, okay, because that's pretty much the domain of my situation, okay. Then you select the smallest number. In this case, it would be 1/3. So then you have 1/3 to 7/6. okay, then 7/6 to what? 2, and then to infinity. Okay, so this is the double chart. These are all the intervals that we're going to analyze. On the right side, on the previous page, okay, we already analyzed velocity, don't you think? And if you don't remember, I'm going to show you here. You already know velocity is going to be positive from 0 to 1/3, negative from 1/3 to 2, and to infinity is going to be positive. So you have that it's going to be positive here, 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 and here is going to be positive. Positive, negative, negative, positive. If you tell me why this, you have two negatives, because this interval, it was 1 in my other chart. Okay? If not, you can replug it in and you'll get the same thing. Okay? Now, we're going to plug any value in acceleration. Okay, so acceleration is this guy that you have over here. So if I plug any value between 0 and 1/3, you have that is going to be negative. Okay, if I plug any value between 1/3 and 7/6, here it's going to be what? That's going to be also negative. And then if I plug, let's say 1.5 here, that's going to be positive. And if we plug, let's say 3 over here, what's going to be that? Positive as well. So now, what are we expecting? So you were expecting that speeding up, okay, let me zoom out a little bit so you can see the situation of speeding up, is when velocity and acceleration have the same sign. So you can see that here they have the same sign, and here they have the same sign. Okay, you might tell me, oh, but it's negative. It doesn't matter. Okay, they have the same sign. So this is how you are going to conclude in this situation. The particle, okay, the particle is speeding up. Speeding up, okay, on the intervals. What are the intervals where it's speeding up? It's 1/3, 7/6 union to infinity. Why this is happening? Because, okay, acceleration and velocity, you need to mention both, one is not enough, okay, have the same sign there. Okay, you need to mention that they have the same sign, otherwise it doesn't make any sense. Are we okay with that? Similarly, you might ask me, oh, what happens if it's slowing down? If it's slowing down, you know that here they have opposite signs, and here too, so you can say the same situation, it's slowing down on this interval, union this interval, because acceleration and velocity, they have different sign or opposite signs. It's even better. Okay, and that's it for particle motion. I hope that you find this video helpful. Bye.